Hello, everyone. My name is Jamila McCrae, and for my presentation, I will be discussing the requirement prioritization technique called quality function deployment. So, just a brief description on what prioritization means in requirements engineering. Basically, it's the process of figuring out which requirements are necessary, which ones are optional, and which ones are not required to have. And in doing so, you must meet the expectation of all of the stakeholders involved, as well as addressing and minimizing any conflicting requirements. And the goal prioritization is to create a list of features organized by which ones are most important and which are least important. So again, the technique that we'll be talking about is the quality function deployment, which I will be abbreviating to QFD for short. So basically what QFD is, it's also referred to as the matrix product planning approach. And in this type of prioritization technique, um, you would be you'd be generating a list of customer points or hearing the voice of the customer to identify like what are their needs and what are their expectations. And once you have that list generated from the customer, you would create a list of design parameters, which are measurable product characteristics that kind of relate to each one of the customer's points. And when we're talking about customer's voice, we're thinking of just something a one word description. So, for example, if the product is a car, the customer would think, I want my car to be fast. I want my car to be big. I want my car to be cheap. And using those one word, like uh, quality descriptors to create your design parameters. So here's a template of the House of Quality model. So on the leftmost part of the template would be the voice of the customer, and these would be those one-word characteristics that the customer would use to define what type of product that they want. And to the right of that, we would have a importance scale, which would be rating each one of the customer's priority from a scale of 1 to 5, with 1 being the least important and 5 being the most important. And from there, we would get the sum of all the importance values to create a percent importance based on how much importance you assign to each of the priorities. And then within the relationship matrix, that is where we compare the engineering team's design parameters and compare the association between that and the priorities listed from the customer. And within that, we'd be creating an association scale. So we're rating the level of association between the design parameters and the priorities of the customer from strong, medium, weak, or 0. And then at the top of the house, we have the interaction matrix, in which we compare each one of the design parameters to another to see whether each has a negative correlation, a positive correlation, or no correlation. So for the example that I decided to cover just to show how QFD can be used, I decided to focus on outdoor roller skates. And just some assumptions and background information. So when I refer to the boot, I'm talking about the part of the skate where you put your foot into, and the truck is the metal component under that where the wheels are attached to. And for the wheels, we will assume that a firmer wheel is better for a smooth surface and a softer wheel is better for outdoor surfaces. And when it comes to the assembly, so the product that the customer will be receiving, the product will come fully assembled with the customer not needing to make any adjustments. And we're going to assume that the user wants to skate for outdoor casual purposes. So here's a write-up of the House of Quality design using outdoor roller skates as the product. So under customer's voice, I listed some simple descriptions: lightweight, supportive, fast, stylish, affordable, and durable. And for each one, I gave them an importance rank, again, from 1 being the least and 5 being the most. And then after getting the total of all the importance, I assigned each one a percent importance based off of the total. And to the right of that, we have our engineer design parameters. So we have weight of boot, firmness of wheel, cost of production, tightness of trucks, coefficient of friction between the wheel and the ground, and speed. And then you would just go across the list and seeing how associated is lightweight compared to each design parameter, and continuing down the list from there. So the scale that I decided to use for the association, I used a completely fold out circle to show a strong association with a value of 9 associated with that. I used the half filled out circle for a medium association with the value 3. For a weak association, I have a quarter shaded circle for a value of 1. And for no correlation, I put a value of 0. So for example, if you're looking at the association between the weight of the boots and the quality lightweight, since those are highly related to one another, I gave that one the fully shaded out circle. And for another example, if you're looking at stylish, the style of the shoe compared to the tightness of the truck, because those are not related in any way, I put a 0 association between those two. So once you have that entire matrix filled out, you would take the value of association that you gave for that one. So again, if it was the filled out circle, you put the value 9, and you'd multiply that by the percent importance. So again, for example, if you're looking at lightweight and weight of the boot, because those are highly associated, I have the value 9, and I multiply 9 by the 10% from the percent importance to get a value of 90. And you would continue to fill out the matrix based using those formulas. And then at the end, you will give each column the total percentage for each design parameter. And then same as before, you would give each one a percent importance based on the total amount of all of the design parameters. And then moving to the interaction matrix, it's very similar. So I listed out the design parameters previously stated, so weight, wheel firmness, production costs, tightness of trucks, coefficient of friction, abbreviated as mu, and speed. And for the legend, I used a double plus sign to show a strong positive correlation, a single plus sign for a slightly positive correlation, a 0 with a line through it for no correlation, a single minus sign for a slightly negative correlation, and 2 minus signs for a strong negative correlation. So again, for example, if we're comparing the speed of the skates to the weight of the skate, because we're saying if the weight were to increase, the speed were to decrease and vice versa, I rated that as a strongly negative correlation. And then if we're looking along the x-axis where I listed out each of the design parameters, I added a up arrow or a down arrow comparing on what we would want our ideal skate to have. So for example, ideally we want the weight to be a lower value. We'd want the tightness of the trucks to be low, because if the trucks were too tight, then the wheels would turn slower, you can't turn as good. And we want the speed to be high because the user wants a skate to move them quickly. So based on the example that I showed you guys previously, I created a list of prioritizations, and I made this list based on the present importance. So listing number 1 as the highest having the highest percent importance as cost of production, and then going from there, we have tightness of trucks, speed, firmness of wheel, weight of boot, and the friction between the wheels and the ground. So just talking about my experience using this technique, I listed out some advantages. So for example, this technique does a good job at translating the subjective customer values to something that is objective and a measurable parameter. So in doing so, we're taking words that might have some emotion tied to them and assigning them to a parameter that's actually measurable. So we can determine the customer satisfaction based on how we're meeting that design parameter. In addition to that, this technique promotes agreement between all of the development team staff. because when it comes to determining the association scale as well as the association between each characteristics, we would need agreement between all the team members because realistically, we would have more team members doing this process with more conflicting ideas. And the matrix also serves as a good comparison tool when you're comparing, your own product to other competitors' products. So you can compare the speed of your boot to the speed of another roller skating's boot, and just do that for each characteristic, and you would have an actual number value that would determine, how well is each component being met, and making sure the most important components are being met. And a few disadvantages to using this strategy is, for one, it is a bit time consuming. So my example did take about 40 minutes. And you can imagine that a team with more people, it could leave room for more interpretation and debate. And this strategy is a bit dependent on the voice of the customer. And usually these values, for example, can be retrieved from doing a customer survey. And as we learned with doing surveys, sometimes the results reached from a survey might not be representative as the customers as a whole. And with this approach, it doesn't do well with changes to customer value, just because introducing any more characteristics will require more calculations when it comes to importance percentage and level of association for that individual value, as well it would change the relative importance for all of the existing values. So if you were to introduce a variable that we saw as more important, it might cause us to rate other values as less important. And when it comes to these one word descriptions, they're a bit narrowly defined and can leave room for interpretation. For example, when the customer mentioned they want their wheels to be fast, does that mean are they going fast in a straight line? Are they turning fast? Are they stopping fast? There's a lot of different ways that one could interpret that. So just a summary of all the key features of QFD. It's a systematic and mathematical approach to prioritizing the requirements, and it focuses on having key features being the importance percentage, association scale, and using the house of quality template to show all the correlations and relationships between what the customer voices and what the engineers determine to be their design parameters. And I would say that this approach would work best for a smaller team, ranking values that have a low chance of changing just to avoid having to go back and make corrections. Here are the list of references that I used. And thank you again for watching my presentation. Again, my name is Jamil McCrae, and I look forward to reviewing my classmates' presentations as well. Thank you.